This is the 7th video for CIS 351, Grand Valley State University's course on computer organization and assembly language. In the first video, we saw how to build a physical device that can perform computations. In the previous video, we saw how the technique used in the first video is only practical for small circuits. In this video, we'll look at a more general approach for constructing circuits. The circuit we constructed in the first video had a very specific pattern. The inputs were connected to NOT gates, and then the inputs and NOT gates were connected to AND gates, and then the AND gates were connected to OR gates. However, you can connect gates in almost any way you like. For example, this is also a valid circuit. Now, one way to formally describe the behavior of a circuit is to use a truth table. To fill out the truth table, set the inputs, and then trace the values through the circuit. So for example, let's put the values 0, 1, 0 on the inputs and see how the circuit processes that. So the first thing that will happen is the OR gate will see the 0 and 1 as input and produce a 1 as output. And now the AND gate sees a 1 and a 0 as input and will generate a 0 as output. So now that we have the output for this input, we can add it to the truth table. Let's look at another example. This time, we'll put 0, 1, 1 on the inputs. And again, the OR gate will see that 0 and 1 as an input and produce a 1 as an output. This time, the AND gate will see a 1 and a 1 as an input and produce a 1 as an output, allowing us to put a 1 in the truth table for that row. So at this point, I suggest you pause the video and see if you can fill out the rest of the truth table. This is what I came up with. Check your answers against mine, and if you can't figure out how I got my answer, bring that up in our next in-person session. All right, let's look at another example. This time, notice that there are some dots in the diagram. These dots show where there's a physical connection between wires. In contrast, if you see two wires crossing without a dot, that means that those wires aren't connecting and they're just passing by over or under. Once again, I suggest you pause the video and try to fill out the truth table. This time, instead of working through the circuit in the slides, I am going to use a digital logic simulator. In particular, I'm going to use a digital logic simulator called JLS. It's one of many simulators that you may run across. This particular digital logic simulator was written by Dave Ploplowski, a professor who recently retired from Michigan Tech. And so like most digital logic simulators, what you'll do is you'll create a new file. I'll just call it test circuit. And then what I can do is drag and drop the different gates I want to put into my circuit. So I'll put a couple of NOT gates here, and then I'll put in a couple of AND gates. And then I can drag wires between them to connect them. And then finally, I will finish up by adding some input pins. We'll give the inputs a name. We'll just call them A, B, and C. And then we'll also add a display for the output so we can see what result the circuit generates. Now, hopefully that gives you a quick idea of how JLS works and how you can drag and drop and connect circuits. What you should see here is we have the same circuit that we have on the slide. But this time we can actually simulate the circuit instead of having to figure it all out by hand. So in JLS, the way you do that is you create an element called a signal generator. And inside of the signal generator, you spell out what values you want on your input pins. So for example, I'll say A0 end, B0 end, C0 end. You can see the pattern there, the name of the input, the value you want on the input, and you need to have that word end at the end of each line. Add that to your circuit, and now you can go up to simulator and say run. And there's a couple of things you'll see here. One is you'll see the output. In this case, given inputs of 0, 0, and 0, your output will be a 0. But you can also see how that signal propagates through the circuit. You can see that A, B, and C are 0 because the wires are black. But for example, the output of this NOT gate is red, as well as this NOT gate, indicating that there is a 1 on these wires. And then here, if we look at this AND gate, we see that its inputs are 1 and 0, so its output is, of course, 0. And same with these other two AND gates. So what I'm going to do is I'm going to add a comment to this circuit. That is this text box here. I'm going to use this comment for my truth table. So I'll have columns A, B, and C, as well as a column for the output. And as we just saw, inputs of 0, 0, 0 produces 0 as output. So I'll just set this off to the side here. And now we want to work on the next row of the truth table. So I will modify this input generator so I can test 0, 0, 1. That would be the second row of the truth table. So I'll put that in and I will run the simulator. And this time we can see that the output is 1. In this case, the second input is a 0. It's a 1 when it comes through the NOT gate. The third input is a 1, so we have two 1s here, a 1 here. That causes a 1 out of the last OR gate and a 1 for the output. So I will modify my comment and fill in the second row of the truth table. We'll do one more. I'll modify it. We'll put in the third row of the truth table, 0, 1, 0. Run the simulator, and we can see that the path through the circuit has changed. Different wires are 1s and 0s, but the result is the same. It's a 1. And we could proceed on to simulate all of the different inputs. For sake of time, we'll just go back to the slide and see the truth table filled out. And once again, if you aren't getting the same answer that I got, let me know and we'll go through that in one of our in-person meetings. Now, the AND gates and OR gates in these two examples all had exactly two inputs. But as we discussed in the very first video, AND and OR gates can have as many inputs as you'd like. For example, in the is prime circuit we built, all of the AND gates have 3 inputs and the OR gate has 4 inputs. The number of inputs that a gate has is called its fan-in. And in theory, there's no limit to how big the fan-in for any individual gate can be. However, there is an actual practical limit when it comes to physically building the circuit, based on the properties of the electronics you're using to build the gate. And as a general rule, the more inputs a gate has, the slower it will be. If you want to think of it intuitively, there's just more work to be done or more logic for the gate to process to figure out what the answer should be. Also, as we saw in the second example, the output of a gate can be used as the input to more than one gate. For example, input A is routed to both this top NOT gate as well as the second AND gate. Similarly, the output of this NOT gate is sent to both the second and third AND gate. As you may have guessed, the number of different places the output goes is called the fan out. And once again, there's no limit in theory to the fan out of any individual gate, but in practice, when building a physical chip, your fan out is limited by the strength of the signal that gate produces. In some sense, the more places you send that signal, the more dilute it gets. And if you dilute it too much, then the chips receiving that signal as input may have trouble detecting whether it's supposed to be a 0 or a 1. Let me also mention that a circuit can have multiple outputs. So in this case, we have 2 outputs, O1 and O2, and nothing really changes other than there's an extra column in the truth table. You just need a separate column for every output pin. So at the beginning of the video, I mentioned that you can connect gates in almost any way you like. So let's talk about that almost part. There are 2 key rules to follow. First, each input has to have a single source. If a gate's input has multiple sources, then how does the gate know what the input actually is? For example, in this circuit here, the AND gate is driven by both input B and input C. So if B is 0 and C is 1, then should the AND gate read that as a 0 or a 1? How does it know what the output should be? So given that there's no obvious, sensible, well-defined behavior, we just say that this isn't allowed. The other rule is that in general, there should be no loops. By that, I mean a gate's input should not be influenced by its output. And that's precisely what we see here with the red wire in the circuit. That is, the output of the OR gate eventually leads back to its second input. And although that's technically well defined and we can do it, it's usually not what we want. Now notice I've been using some weasel words here like usually and typically and rarely and so on, because there are a few cases where it does make sense to have feedback in a circuit, and we will look at those next week sometime. But for now, we're going to stick with these two rules that each pin can only be driven by one source, and we're not going to allow loops. So if you follow those two rules, then you have what's called a combinatorial circuit. And it's called a combinatorial circuit because the output is always a combination of the input. And so every time you run this circuit with a given input, you always get the same output. For example, when you put 5 into the is prime circuit, it always says true. And when you put 6 into the is prime circuit, it always says false. Now, you might find this an interesting distinction to make, right? Because, well, how could a circuit behave any differently than that? How could it not give you the same answer every time? And again, we'll get back to this in a week or so. But as a quick preview, it turns out that if you do have feedback, if you do have loops in your circuit, you can use those to create memory. And if your circuit has some sense of memory in it, then the value it's storing can also affect its output. A circuit that has memory like this is called a sequential circuit. And in that case, it doesn't always give you the same answer. But in any case, we'll get to that soon enough. So let's quickly summarize the key points of this video. So the main point is that logic gates can be connected in many arbitrary ways. We don't have to follow that big hammer pattern that we started out with. And when you're given a circuit put together this way, the truth table is the formal description of what this circuit does. It tells you exactly what the output should be for a given input. And as you build these circuits, remember that they can have multiple output pins. We've been doing a lot of work with circuits with just one output pin, but you can have as many as you'd like. You just have to add a column in that truth table for every different output pin. Also remember that gates can have an unlimited number of inputs. This number of inputs is called the fan-in, and a gate can be connected to an unlimited number of other gates, and that's called the fan-out. There are some practical limits when you're physically building the circuit, but from a theoretical standpoint, these numbers are both unlimited. But even though a gate like an AND gate or an OR gate can have multiple input pins, any individual pin can only take a signal from one source. We don't want any conflicting signals coming in. And for the most part, circuits shouldn't have any loops. And when you're building a well-defined circuit with no loops or no other way of having memory, we call that a combinatorial circuit. So those are the key facts that might show up on a homework or an exam. The other thing you may be wondering is, what might I ask you to do with this information? And so here are the key things you might want to work through. First, I'll likely give you a combinatorial circuit and expect you to fill out the truth table. Or maybe we'll go the other way. I'll give you a truth table and I want you to show me how you could implement it with a circuit. I might also just ask you for a gate's fan in and fan out to make sure you really understand what those terms mean. So these are the basic ideas of combinatorial circuits. There's a lot more to learn about how to use combinatorial circuits and to design them in an efficient way, and we will cover that over the next several videos.